Video segment is the continuation of the one that I did earlier. I think it was 28, if I'm not mistaken, and it dealt with the composite plate, as shown here, which is clamped and then it's subjected to a sinusoidal load. Well, let me put this thing in the slideshow mode, and then we'll talk about it in more detail. Okay, so the subject that we're going to be discussing in this video is a harmonic response of a laminated composite plate under a concentrated force. And the previous video that I did, the the magnitude of that concentrated force was always kept constant, okay, irrespective of what the frequency of the applied load was. Okay, here, we're gonna assume that the magnitude of this load will actually depend on the frequency, and I'll talk about that in a second. Now, by the way, this business, depending on what resources you look at, they may be called harmonic response, frequency response, sinusoidal response, or steady state dynamics. These all mean the same thing. We're gonna apply the we're going to apply our problem or the loading to a geometry of this type. So it's a symmetric laminate plus or minus 45 degrees, and the dimensions are given to you in a minute. It is symmetrically located about that reference axis. Now, the source of a problem like that is, for example, if you took a fan, a table fan, or a rotating machine, could be pump or a compressor, etc., and put it at the middle of this plate, okay, we know that as due to the imperfection in the manufacturing, there is probably an imbalance. That's why there is an imbalance with this rotating machine, with this fan, and that as it turns, it causes a centrifugal force, which is going to be applied at the center in an up and down direction. Okay. By the way, I've drawn here my rosette along with the global coordinate system to make it easier to see. Now, this geometry and the data that I'm going to be taking is taking out that book, and in fact, I did a video segment on applying a static load to this problem. Okay. Uh, Now, the geometry is 50 centimeter by 50 centimeter composite plate, and the total thickness is four of them. Total thickness is 5 millimeter, and the properties are given here. I also obviously need the density because it's a dynamic problem, so we put it there. Now, so in general, this amplitude, the amplitude can depend on frequency. If it's like the previous video segment, but it was constant, then of course this is going to be a constant value, and we for a constant amplitude, irrespective of the frequency, we can use a white noise modulation type that we discussed in the earlier one. But if it depends on omega, if it depends on the frequency, then we have to provide CATIA with our own modulation, which is in the form of Excel spreadsheet or a text text document, text file. So here's my fan. I'm going to be investigating the rotation of this fan, the RPM of this fan, or actually this is converted to hertz, between 100 hertz and 300 hertz. This may not be a realistic range. It's very close to it, but anyway, we'll consider that. In your vibrations course, you may have seen this thing in the context of a diagram like that. So you have a rotating machine up there, which has a mass imbalance and is at the distance placed, which can be assumed to be placed B units away from the rotation center. And as it turns, it creates a centrifugal force, and that centrifugal force actually causes this thing vibrates up or down. It also can go sideways, but a vibration up and down is what is the critical one. Now, uh, the, the magnitude of that concentrate force is actually the mass times r omega squared, okay? So r being b here, mb. So my mb, the one that I'm going to be using, is assuming that there's a 100-gram mass in mass and at a distance of what is that, 2 centimeter away from the center of rotation, and then if you do mb omega squared, if I convert these things to hertz, omega is going to be 2 pi f, and if I take the 2 pi out, so it's going to be 0.0079 f squared. F is the frequency in hertz, okay? So I'm going to be using this number, not ignore the f squared, this number as the applied load in the static situation. And then we remember that when you do these dynamic problems, you have to do static K. I have done it by doing static first and then insert or extracting frequencies of vibration, frequencies, natural modes of the structure, and then we do insert dynamic, harmonic, transient dynamic, okay? Which we're going to do that. So the way my modulation is going to be a curve like that, okay? This is an Excel spreadsheet I'm going to prepare. Although I have it, but I'm going to prepare it from scratch for you. So it goes between 0 and 300 hertz, okay? 0 and 300 hertz, yeah, and somehow stop there. And it goes, the height goes from 0 to magnitude of 1 or amplitude of 1, okay? This is how you do that when you have to import frequency modulation. So you go to the modulation toolbar, and then you make sure that you select the frequency, icon here, and then it asks you to go and get your Excel spreadsheet. Okay. Now this is the modulation curve that I'm going to be creating. Goes from 0 to 300, and height goes from 0 to 1. Now, let me remind you what the steps are. You create the geometry, you create the plies, you do a static analysis. When doing static analysis, you put restraints on the edges of the plate and you apply load at the center and you run it, of course, and then you insert a frequency case, and that will extract the natural frequencies of the structure based on the restraints that you put in there. It has nothing to do with load, and then you insert a harmonic a dynamic response case, and that uses the frequencies that you calculated and the excitation or modulation that you provided based on that load. Okay, and yeah, so this step uses the frequencies here and the load that you already put in static, plus the modulation that you're going to submit as a Excel spreadsheet. This CATIA's time dependent or frequency dependent problem is based on modal superposition, therefore you cannot do nonlinear problems with it. Okay, so let's go ahead and do this. I'm going to do everything from scratch for you, although that means there will be repetition because creating this structure we have done it 3 times in the previous videos. If you feel comfortable with it, you know how to do the material properties, just fast forward the video and move on to the stuff that you don't know. Okay, so let me go ahead and go to CATIA. Move this thing down. Go to CATIA. Let's do the material first. So we go start, infrastructure and material. This is a new one that we're going to create. I double click on this and give it a meaningful name that I can recognize. I'll call it rotating fan. How about that? Rotating fan. Okay, apply. You can see that the name, oops, what I did. Try it again. Rotating fan. Fan. Apply. See the name change here. And then you go to composites. The thickness of each one of those layers is 4 plies, 125 centimeter, 0.125 centimeter, and it's a unidirectional, although these are totally irrelevant for us. We just need this number, 0.125. And then we're going to go to analysis, and it's 2D orthotropic. We are doing, plies in that context. The numbers were the first one was 1.48 e to the 11. The next one, transverse direction, is 1.05 e to the 10 Pascal. Poisson ratio is 0.3. This is the data from that book. Shear modulus, it's the same for all three of them, 5.61 e to the 9, and same thing for the other two directions. 5.61 e to the 9, and same thing down here, 5.61 e to the 9. The density is 1800 kilogram per cubic meter. Apply. Okay. I always check, make sure nothing has changed here. These are good. Now we're going to save this thing. I'm going to save it in that folder, rotating fan. I think it was called rotating fan, yeah. And I'm going to call it, give it a name that I can later recognize, rotating fan. Okay, this is done. And now I'm going to do my Excel spreadsheet. How about doing that first? So the first column, X, is going to be frequency in hertz. You have to do it like this, in parentheses Hz. And the second column has no units, so we're going to Y of parentheses open, parentheses closed, because we don't have units here. So 0, and obviously this is going to be 0. Okay, here let's do it every the data that I'm going to give it every maybe 20. Can't remember what do they have here. I'm doing it every 25 hertz. Okay, so 25. Okay, and then these two I'm going to select and drag it until I reach 300. Okay, so this is equal to this stuff from Excel that you probably know is equal to parentheses, this guy divided by the maximum frequency in hertz that I'm specifying here to the power 2. Okay, and then I'm going to take this thing and drag it down here. Of course, when it reaches down there, it's going to be 1. Okay, so I'm going to save this thing, file, save management. Where would that be? In the desktop, rotating fan. I'm going to did it live. How about that? Did it live. Okay, say okay. And if I plot this, I will get that sketch that I showed you. We close that. Now we're going to do the geometry. So file, new, a part file. I'm going to call it rotating fan. Rotating fan. Okay, very simple rectangle. So you see, in generative shape design, on that plane, I'm going to sketch a rectangle which is 50 centimeter by 50 centimeter. So this is 50, and this is 50. Okay, exit. Okay, and fill this FILL right here, and join it. And I'm going to double click on this thing. My habit is always to have the joining direction down in a problem like this. Okay, so let's save this thing. File, save management. This was the file name, save as, folder rotating fan. Okay, very good. Let's create our access system. This is going to be used as rosette, and I'm going to move it. The default is over here. I'm going to move it a little bit to the right so that I can see it. You put the cursor on origin line, create a point, give it a coordinate, for example, y of minus 20 centimeter, and say preview. So it's going to put it right there, and we say OK, and make sure this is unchecked. So the coordinate system, this is not going to be used until I need it. Okay, good. So now we're going to go to our composite design. All these steps were done in the previous 2-3 videos. Okay, so if you know these things, please fast forward. Composite parameters, apply, add material. Let's go to that folder, get the thing that I created for you. Rotating fan, right there. And this is the one that I created. And we say OK, right here. Okay. For direction, we have 45 and minus 45. I don't need to create anything already. Add a rosette, and the rosette is going to be this fellow. Okay. So the angles that we specify are going to be with respect to the x of this rosette coordinate system. Okay, so save everything. Let's create our ply group right there, ply group, and the surface is right there. Draping direction, I always like up, and we say OK. And now we're going to do first two plies and then use symmetry in order to reflect it and avoid doing extra work. So here is a click on this manual ply on that group. The boundary is this, okay, that sketch, and the attributes is the top one is 45. That's ply number 1. Material is already correctly picked, so you can see that the ply has been created. Repeat this thing again for the next ply. So in that group, boundary is still the same thing. Attribute, the next one is minus 45. Okay, and you can look at this at this point. Although we're not done it, we need 2 more plies. Okay, cancel that. So I'm going to use this icon here in the plies toolbar, this icon which says symmetric ply stacking. You select it. It says what is the group. There is my group, and it's a non-pivot. Non-pivot means there's going to be 2 more below. That makes 4. If I do pivot, there's going to be 1 on top. The one in the middle is going to be maintained, and there's going to be 3 plies. The top one is going to get reflected down below. But I want 4 of them. Notice that create 4, and now you can look at it. It better be 45, yeah, 45, minus 45, minus 45. Yeah, we can see that there's 2 of them down there, and then 45. So we say cancel, and we're happy with this, and save everything. All right, now we're going to go to advanced machine tools. The reason I go to advanced machine tools, I want to make sure that my mesh is nice, quadrilateral type element. If I'm happy with rectangular, triangular one, I don't have to go there. Okay, now we started using this thing in the last video, and I told you that this is something new because so far all the meshes that I've created we're using the surface mesher. Okay, but there's something called advanced surface mesher. There are things that you can do here that you cannot do it in the surface mesher. For example, to make sure that that point that I put in the middle, remember I created a point in the middle of this gadget. I want to make sure that that is a node of the mesh. I can't do it in surface mesher. You have to do it advanced surface mesher. So you click on it. Where is that node? Let me go ahead and get the node because I think it's hiding right now. So there, maybe I can't see it. Let me change the rendering here. Why is this thing not showing up? Let me see for a second. My node is my that point that I created. Oh, oh no. You know what? I think I forgot to create my node at the center of this. I thought I did it, but I'm not. So, okay, this is fine. There's nothing wrong with it. Let's go back to the part design. Let's go to back to part design, okay, and create a point. Well, you can create a point right here, and the coordinates is going to be 25 and 25. I think I forgot to do this. Okay, right there. This is the point that I forgot to. Now go back to advanced meshing tool. All right. So we go to the advanced surface measure, not this guy, advanced surface measure, and it's asking for the geometry to be meshed, which is that join. Now because I hid it, because I choose a different rendering, I can't see it, but right there. So this is my surface. Now on purpose, I'm gonna put a 7 here. And then I'm going to come back and change it to 5 to show you what the effect is. Parabolic element, quads only, we say okay. All right. Now, there is something that we never used before, except for the last video, of course, when I did the same kind of trick. It's this thing, add, remove, constraint. So I click on this. Notice that you don't have this stuff if you do it with the surface measure. You do it, you get it if you do it with advanced surface measure. Now, select the tab, the points tab, and then go and select this point that you created right there. And you say, okay. And now you mesh it right there. This is the measure. That's the same as before. Look at what happened. So it tried to do all quadrilateral, but it couldn't, okay? So it created a mesh, a mesh like that. But that point that I created is still a node of that mesh, okay? Now we exit this, okay? But you know, I can go ahead and remember this was based on 7 centimeter that I inputted. So let's go back here, back there, and change this thing to 5. Okay, say fine. Okay, it says invalidate the geometry simplification. That's fine. I have no problem. Mesh it, and there we are. So stuff like this, you cannot do it, or at least I'm positive you cannot do it in the surface measure. You have to do in an advanced surface measure. Okay, so we say fine. Incidentally, the way you do this, if you don't use a surface measure, you use the regular triangular mesh, is slightly different. If you see some other videos which are unrelated to composites on the finite element playlist, you see what I've done. If you have a regular triangular one and you make sure that a particular point, for example, is a node, what to do. But that's okay. So we exit. All right, so let's save our analysis file. File, save management. There was my analysis file. Save as. This is the right folder. I'll call it rotating fan. Rotating fan. Okay. And we're done here. So we're going to go to generative structure analysis. This is where we apply the loads and the strains and things like that. First of all, let me hide this compass, not compass, rosette. And I'm going to hide my stacking display branch, and I'm going to hide my sketch. The reason is that if these are showing up, I will not be able to put restraints on these edges because I'm picking the, the sketch or the boundaries of the plies. Okay, so let's first of all let's clamp these edges. So 1, 2, 3, 4. All right, and we're going to put a force here, okay, force here, and this is going to get transferred to the node later on. So where is the distributed force? Right there, distributed force. You put it on that, and the magnitude of it is negative 0.0097. Let me see, what is it that I said I was going to put on it? Right here, 0.79, not 97, 79. That's right. Minus 0.0079, and we say that's fine. Okay, it is there, you cannot see it, but it's down below right there. See this has the same effect. All right, good. uh, we save this. Let's import our composite properties. The surface is right there, the support is right there, and we are doing it by ply. So you click on the wrench, you go and select your ply group right there, and we say OK, and it's symmetrically placed about the reference surface. We remind you what that thing means, like that, symmetrically placed there, and we say OK. Now I can run this thing. By the way, notice that when I was doing all of these, the first time that I went to the advanced surface measure, it asked me whether I wanted to do static or dynamic, etc. I didn't change it. I left it as static. This is why right now we have a static case here. We applied our load and everything. We're going to run it. Nothing exciting is going to happen. This is going to go bend down, assuming that we haven't forgotten anything. There. Yeah, look at the deflection. Obviously, it's going to go down. Of course, you can clean this up, do it the way you want. I double clicked it, use average ISO, and you can choose the different rendering, material shading, so that it looks nice in color. Okay, fine. So let me deactivate this. Deactivate. All right, now what was the next step? So when you go here, we created the geometry, we created the ply, we did the static analysis, and now we're going to do insert. We're going to insert the frequency case. So we go up here, insert frequency case, right there. It says, okay, do you want to create your restraints as new ones, or do you already have restraints that you can use? Well, I already have ones that I can use, and I go to the static one that I did here, right there, and it uses those restraints. That's it. Nothing else you need to do. Just run it. This will extract 10 frequencies, and the reason it does 10 frequencies is because the default is 10. If you double click on this guy, notice it says 10 modes. Okay, you want to change it if you want to change it and play with some of those options there. That's up to you. Now let's look at the deflection mode. So you click on the translation, double click, and these are the 10 modes that were extracted. So this is the first mode, here's the second mode, third mode, fourth mode, etc. All the way to this is the 10th mode. Cancel. Put it back there. Cancel. Now, what is the next step? The next step is insert harmonic dynamic response case. Now remember, I created this Excel spreadsheet and I haven't used it. We will. So you go insert. We did the transient in the previous videos, I believe 26 and 27, or 27 and 28. So we did. Let me make sure that I know what we have done. Okay, so just bear with me for a second. The transient one was done in videos 26 and 27. Uh, I'm sure 26, yes, 26 and 27. 26 and 27. And yeah, so insert the harmonic dynamic response. Okay, it says, well, you extracted modes. Do you want to use it? Well, the answer is yes, right there. You have to use it. You have no choice. But the load, you already have it, or do you want to use a new one? Well, we're going to use a new one. Okay, fine. Okay, let me deactivate this plot for you. All right. Okay. Uh, I'm going to check something for you because video number 28 was this problem, except that the amplitude was constant, independent of the frequency. So now we're going to do it with function of frequency. Okay, good. So here we are. First of all, if you double click on load excitation, if you double click on this, it asks for, okay, what about your load? Well, that's no problem. I can go and select this load. In the static case, remember I put a 0.0079 downward? Okay, I can do that. The only problem is that, okay, where's your modulation? If the load was constant as a function of frequency, I can go and create a white noise and use it. But this is not constant. We know that. So I don't have it cancel that. We we go here to the modulation. This is white noise. This is frequency modulation. The other one is time, but we don't have time problem. You click on it, it says, where is it? Well, browse. Remember I created that? Frequency modulation. We did it live together. We say OK, and then we say OK. So it creates it for you in the tree. If you look carefully, you see that it's somewhere here, right there. See under modulation? And in fact, we can plot it to make sure that it's right. So put the cursor there, right click, oh, put it there, put it on the modulation, right click, and then generate 2D plot. This better give me that parabola, and it does. Notice go to 0 and 300, and the amplitude goes between 0 and 1. So we close that, don't need it. All right, so now I go double click on the load. For the load, I go and select it from the static case that I did. Remember that concentrated downward load? And for the modulation, we go and select the one that we created right there. We imported it, okay? We say fine. And this scale factor, what it means is that don't scale up my modulation curve, okay? Just use it as I gave you. All right. Now, believe it or not, you don't have to run it. Everything that you want is already available because after all, what you needed was the frequencies and the load and the curve. In the previous two videos, I also said, okay, let's run it again, but you really don't have to do that. This is why it's so efficient. This process is so efficient. So what we do is we go say, fine, put the cursor there, right click, uh, generate 2D, 2D, 2D display. Okay, yeah, we have done this in 3 times already in the previous videos. Finish. It says, okay, go pick the node that you want to monitor and tell me what is it that you want to plot about it. For example, do you want to do displacement? Do you want to do velocity, acceleration? No, I want to do displacement. Okay, so you minimize this and you go to your screen back there and try to pick that node. Now, if you can't see it, the different ways of doing it, you can change the rendering here. If you still don't know where it is, remember that point that we created? If I say hide and show, it tells you exactly. Just don't show me the join, but show me the point right there. It's right there. Okay. Well, you could have done this thing by just counting these 5 and 5 in each direction. Okay. Add, and we can close that. So it did create it. It's right there. If I double click on it, and this is wrong. Uh, Hertz, maybe actually, let me zoom in. This is wrong because this is supposed to be a parabola, right? Okay, but it didn't go all the way. It didn't go all the way to 300. So let's make sure that our data was correct. So let me go ahead. Things like this happen. We have to make sure that 300 hertz. Okay, so this was good. No problem. Okay, so my data was correct. In fact, I plotted it. It came out to be okay. And displacement node 5. Yeah, that looks good. That was node 5. Okay, so let's go ahead and see. Uh, I have a feeling. Let me see for a second. All right, you'll notice that, let me minimize this for a second. This didn't look right. And it goes between 0 and 10 hertz. And the reason this happened is that when I was trying to do the analysis, it's very, very, very important. You see that under the, if you double click on this, it tells you that the range that I want to sweep is between 0 and 10. So I don't want that. Remember this? I said that I'm gonna look at it in this range. Okay. So what we want to do is we go between 100 hertz and 300 hertz. There's nothing wrong with what I showed you. It's just that the range was so limited that it showed you just almost a straight line. And let's make this thing a thousand, I don't know, 1,000 or 100, 1,000 steps. How about that? Okay. You don't have to run it. Just go ahead and double click on this. And there we are. Okay. So what happened is that you're sweeping this frequency of the fan, the rotation of the fan between 100 hertz and 300 hertz. And as you do that, when that frequency reaches the frequency, natural frequency, first natural frequency of the plate, which is around 179, I think that's what it was, 179, you have resonant. So if you look at it, if you look at your model here, you can look at the frequencies again. The first frequency was 179. This is why when I get close to that, I get a peak. Now, you did not get the other peaks because the next one was at, basically 323, that kind of a thing. Anyway, so let's go ahead and increase the range. Let's see now, where was this? Right there. So we go here, not there. We go to the harmonic dynamic response line, and let's go to 600, about 1,000 hertz. Okay, that's not realistic. A fan does not turn at 1,000 hertz, but we can pretend that it does. So let's go ahead and notice I'm not running it because everything is already there. Okay, there we are. These are the other frequencies. This was 180, and the reason that you don't get a peak at 300 is because that 300 hertz was probably not a transverse. It was not a transverse mode, vibration mode. It was probably in plane or something along that line. These are the other peaks. The other thing is that you notice that it looks like there is damping because otherwise this should shoot to infinity, and the answer is yes. We talked about this in the previous video. Now by default, let me close this. By default, when you go to damping, it takes all the modes and puts 1% damping on it. So I put a 0 here if I don't want any damping. Now just go and look at your curve. Okay, notice that it shoots to infinity. Okay. The other thing that you can do, if you're interested, is that for each one of these, you can plot for each one of these frequency, you can plot the shape of the deformed plate and plot the stresses. So if you go, for example, if you click on this displacement and you double click on this, double click on that, it tells you that you took the displacement at 100 hertz. Okay, so if I go, for example, I don't know, some other at some other frequency, you can look at the displacement. Okay, and if you want to, I'm not going to look at these, but if you want to look at the stresses, you put the cursor right there, harmonic dynamic, right click, generate image, the stuff that we have done in other videos in different contexts. So stress component, for example, we say okay, and if you want to know what is it that you have to plot it, what is it that you have plotted, you double click on this line which says stressful tensor. It says that, oh, you have plotted sigma x in the local direction. So sigma x in the local direction, and oh, this was translation, right? Yeah, okay. So what is this stress? No. for lamina 1. You can go to the other laminas and find out how things look like there. Okay. So I hope this helped you to understand the how to do process for analyzing things like that. I do realize that we are not checking things against experimental result or theoretical results, but if you did have it, it's a good idea to go and find out what's going on. Okay, it's easy to generate good-looking graphs, good-looking colors, that they may all be garbage. Okay, so just because you're getting things on the screen and they look good doesn't necessarily mean they're right. Good luck.